All right, welcome back, guys. So we did not quite finish chapter 9, which was our T statistic, right? Yes, we had started the T statistic, and we didn't quite get, just like with chapter 8, we didn't actually get to the effect size. So it's funny that in both cases we didn't actually get to the exact same point. So I'm going to pick it up from there. We're going to talk about Cohen's d, the estimated Cohen's d, and then confidence intervals as well. So let me go ahead and switch over. Okay, so the last thing that we talked about, we had went through hypothesis testing, right? Going through each of these steps for the T statistic, right? We are no longer talking about the Z statistic. The T statistic changes based on the degrees of freedom that you are using. We went over some assumptions that you have to go and ensure are correct, such as your sample has independent observations, and the sample has to be, the population that you're sampling from has to be normally distributed. Talked about how sample size and sample variance affect the T statistic as well as the estimated standard error. So let's go talk about the effect size. Okay, so just like with hypothesis testing that we had set up for z-scores, we have an effect size that we can measure for the T statistic. So this up here is our general formula for Cohen's d, the mean difference over standard deviation, right? When we are going to be using the T statistic and doing an estimated Cohen's d, we still have the mean difference. So we have our treatment subtracted from the population without a treatment. Or like I was telling you guys, if you do not have the population mean, this can be something, for example, in your studies that is logical, or that would be a good baseline to use instead. How much are they deviating from the baseline, and is that significant? Is there enough of a shift? But the change that is happening here with the T statistic is we are not using the standard deviation, we are using the sample standard deviation. So we do not have the population standard deviation, right? That's the whole point of going into the T statistic, is we do not have that population parameter. So here we're going to be using our data and using the sample standard deviation. So for example, if we talk about that example we did in class, if you have an e-reader and you read at bed at night off of your e-reader, is that going to affect alertness the next day? We had went through the hypothesis test, and I think we actually rejected the null hypothesis that your alertness levels drop if you're doing this. So we went through that, calculated the T statistic, rejected the null hypothesis. But that only tells us that there was a significant effect, not how strong the effect was. So again, effect size, Cohen's d, is reflecting the strength of your treatment. So mean difference over a sample standard deviation, no longer the population standard deviation, so sigma. So we had actually the variance calculated when we did the T statistic. So in order to get the standard deviation, we just take the square root of that. So we had a variance of 20, take the square root of that, and we get 4.5. We can plug that into our formula for the D calculation. So mean difference over 4.5 gives us 0.89, which is actually pretty big. If you look back here on the magnitude of D, where would this fall in? It is very large. It is definitely in this category of 0.8 that corresponds to a large effect. Okay. So to go through another example, not the entire hypothesis testing, but just trying to calculate the estimated Cohen's d. So we have a sample of 16 individuals with a mean of 40. The sample you get has a mean of 44, so difference here of 4 points, and we're given the variance of the sample. So assume a two-tailed test with alpha 0.05, nice and conservative, pretty much the go-to configuration we want. So what they're telling us here to do is compute Cohen's d, compute the effect size. So write out all of our numbers. What we have here are all the different elements that we would need. So one thing is to calculate Cohen's d. That's here. Our d formula. In order to get the sample, we need to take the square root of the variance. But we can also go and calculate the other portions that we would need to figure out if we're going to reject the null hypothesis or not. So this is our formula for the standard error. The estimated standard error, I'm sorry. I'm getting tired. I'm recording much later than I normally would. It's like almost 8 o'clock. The estimated standard error, yes. I don't know why I'm brain farting right now, because, yes, because the regular standard error is going to be sigma m, but this is the standard deviation of your sample, so SM is going to be your estimated standard error. Sorry for that hiccup. So we can use this formula because the estimated standard error needs to be plugged into the t formula for our t statistic. Okay, so let's go and calculate first the estimated standard error. We plug in our variance up here, which is 16. We plug in our n, which is also 16, so we get an estimated standard error estimated from our sample, not the population, of 1. For the t statistic, we can plug in our values that we have here, right? So estimated standard error goes down here. So a difference of 4 over 1 gives us 4. So this is your t statistic. Now, if you think back, do I have it here? No, I don't have it coming up. But on this example here, you know, if you looked at the table, the t distribution, the t table, you can look up your DF here, and I actually, I did it wrong, I'm sorry about that, but your N is 16, so your degrees of freedom should actually be 15, not 16, so I selected the wrong row here. But you can move over to two-tailed, 0.05. The t statistic for degrees of freedom of 16 would be 2.12. If it's 15, it's going to be a little bit higher than that, just like a smidge higher. But you can see 4 is going to be significantly larger. So this is the critical t. If we are larger than the critical t that we get from our t distribution, then our actual calculated t, if that's a lot larger, we can reject the null hypothesis. Right? This is what we were doing in class when with the z-score, if our z is a lot larger, and in the critical region, because of the z that you get, either 1.96 or 2.58. And off the top of my head, I can't quite remember what 3 z's would be. I think it's 3.3 something. So nevertheless, here we're rejecting the null hypothesis based on the information we're giving because this t statistic is well beyond. To calculate Cohen's d, it's the same mean difference as what we were calculating for the t statistic, but now we're not doing the estimated standard error. We're doing the, seriously, my brain. I should not record late at night, I'm sorry. It's going to be your standard deviation, right? So we have our variance here. If you take the square root of your variance, so I have that down here. If you take the square root of your variance, you get the standard deviation. Gives you 4. So your d, your Cohen's d is 1, which is very large. So not only did you reject the null hypothesis, but you had a large effect size because we said anything around 0.8 or above is going to be a large effect, and 1 is definitely going to be in that category. So that's Cohen's d, and you can calculate that, and that's perfectly fine. There's another thing that we can do, especially when it comes to the t statistic, and that's going to be called variance explained, which is r squared. And this is also going to keep reoccurring whenever you guys go into stats 2 and you start doing ANOVAs. R squared is going to be coming up again. So another way to look at treatment effect, how strong was my effect, is instead by not calculating Cohen's d, but asking how much of the variability in the scores is explained by the treatment effect. So the variability in scores, right? People are different. We get a normal distribution. Some people are on the top, some people are on the bottom, but most people are in the middle. So there's already natural variability. But when we have that shift from a treatment effect shift moving over. Not everyone is going to move over equally, right? We expect it to, but that's not actually of what actually happens. So, in, for example, a distribution like this, 50 would be your population mean. After our treatment, we get a mean of 46, so that's a 4-point difference. And just looking at how these numbers are spread out, you can see they're mostly centered around 46 and not centered around 50. So one thing that we can do, just first look at this top one here. These are the original scores, including the treatment, showing how much they are deviating from the population mean. So our population mean here of 50, draw a line for each value showing how much it's deviating from that population mean. You can see most of them are down here. What we can do is we can, my mouse sometimes moves forward when I don't want it to. We can create a shift, we can adjust the scores by adding in the effect, or rather by, not adding in, by removing the effect out of that. So if you took all of your values and you added 4 to each of them, and you shifted it to where they would be centered around the population mean, how does the variability look then? So now we're centered at 50, now you draw out your lines, and these are the adjusted scores if we remove that treatment effect. The treatment effect being 4 points. If we remove that and we shift it to the population mean, this is what it looks like. So deviation scores are going to change. The sum of the deviation scores are going to change, meaning the sum of squares are going to change. So over here, this is calculating the sum of squares if we include the treatment effect. So raw scores here, no adjustment was made. How much are they deviating from 50? So minus 11, right? Most of these are minus. Square it because we just can't simply add them all up. So we square that, we get a sum of squares of 306. Now, if we do that extra calculation of removing the treatment effect, so we have to add 4 to every single treatment or to every single value, that will shift it to be centered around 50. It will shift the distribution, right? You're not bringing up 39 person all the way up to 50. You're just shifting it according to how much the treatment effect, the hypothesized treatment effect would be, and therefore removing the variability of the treatment out of the actual variability of these people. So now your deviation scores change, and the sum of squares for these deviations is lower, or rather significantly different than the sum of squares for if you didn't do that. So sample variation is normal, right? Not everybody is going to have the same score, and that's perfectly fine. We ideally want a small variability, right? If we have small variability, then we can more confidently talk about the shifting of the distribution of it being a true treatment effect. But nevertheless, people are different. After treatment, people generally move towards the direction of the effect, but not everyone shifts equally. So if we remove that shift, meaning remove that treatment effect, we still have some variability left over. So we can do this calculation where we do the total variability minus the variability that's not explained by the treatment, and that's left with the variability that is accounted for by the treatment. I know that's a lot, but let me show it to you like this. So variability accounted for by the treatment effect, actually, here. Sorry, I'm all over the place. I really shouldn't record at 8 o'clock. I'm sorry, guys. The R-square calculation. So this is not Cohen's d. This is going to be a separate way of calculating treatment effect. R-square is a ratio of your variability accounted for by the treatment effect, right? This is the sum of squares that you had removed over the total variability. This is a percentage where we now get 47%. We can explain 47% of the variability in our sample because that was our treatment effect, right? The rest of the variability, going up to 100, that we cannot explain because that's stuff that's contributing to people being different, right? Whether that's their size or their gender, their cognitive abilities or whatever. People act differently. The treatment is not going to equally affect everybody. But when we talk about that shift in the treatment, we can actually calculate how much of that variability is due to the after treatment scores, how much of that variability is due to our treatment or due to their naturally occurring variability. So the R-square addresses the variability that came from your treatment. Okay. So formulaically, the way that we have this is t squared over t squared plus the degrees of freedom. We can plug that in from our prior example. We might get something here, 0.47. And we might write it like this if we're going to write it up. The participants had an average of 46, like alertness scale, standard deviation on a standardized alertness test. If they were doing nighttime reading, then their score was significantly lower than the general population. So T, including the degrees of freedom, what was the T statistic? It was significant at an alpha level of 0.05, and this is where you can report the R-square now. Okay. So just like the Cohen's d, we're going to have different levels at which we say this is a small effect, a medium, or a large effect. 0.25 is already considered a large effect. So if we have something like 0.47, that is pretty significant. That's a large effect that we got. So this score doesn't really have an effect on Cohen's d. They are just two different ways of looking at the treatment effect. One being the variability after that treatment has happened. How much are they varying? Was that because of your treatment? Or was that because people are different? Cohen's d is going to be a different way of addressing that based on the mean difference and the standard deviation. Or if you're using estimated Cohen's d, estimated standard deviation. Or rather, sample standard deviation. Okay, last bit. This is this the last bit? I think we have one more thing after this, but constructing confidence intervals. So far we've been in this region, the tails, your critical region, right? If I'm out here, that means I can reject the null hypothesis. But you can do the reverse too, especially if you don't know the population mean, right? We might not actually know what mu is. And I've been hinting at this. Most of the time we do not know what the entirety of our population is doing. But we can use enough of our sample statistics to put something together. And in this case, confidence interval is you saying, I am 95% confident that the population mean is going to fall within this interval, a lower bound and an upper bound. So we're going to be using our T statistic. If we just change our formula to solve for mu in particular, we're going to have our sample mean minus, right? This is just like when we have solve for x, solve for m. Here it's just going to be solve for mu. Our t-score times the estimated standard error. It's going to be plus minus because we want a lower bound and an upper bound. So late time, this is the same example as we've been using before. Late night reading. Mu is unknown, but we have our n, how many people we collected, our sample, and our sum of squares. So we're going to use a t for a 95% interval. So we can actually, in the table, in the t distribution table, look that up for a degrees of freedom of 8, right? Because it's 9 minus 1. And we're trying to look up what is the corresponding one for, would end up being a 0.05, right? You'd have to look it up in the column for two-tailed 0.05. That would correspond to 2.306 here. Okay. So m plus minus t times the estimated standard error. So we have M because we collected that data, 46. T, we can calculate, or rather, no, I'm sorry, we don't calculate that. We get that from basically that critical region, looking up in the table. And then we had already calculated before, that's what I meant to say, our estimated standard error. So what we get here is 1.5, plug all these guys in. So we get 46 plus minus 3.5. So this is our confidence interval, a range going from 42 to 49. We can say that we are 95% confident that the score for the true population of bedtime e-readers have this alertness score. So this is not only going with the unknown of no population standard deviation, but also no population mean. So then we can talk about, well, we are pretty certain, meaning 95% confident, that it will fall within this range, right? We can also talk about, I am 99% confident, and then you would use a two-tailed test with an alpha level of 0.01. So you would look that up in the table, figure out where the column for 0.01 is, and then go down to your degrees of freedom that matches how large your sample is, that t statistic, then you plug into the formula times the estimated standard error to figure out how large that, in actual numbers, how large that confidence interval is. Okay, so that was the effect size. We can do that through Cohen's d or our new one, r squared, which is the variance explained from the treatment, as well as confidence intervals. I didn't actually put this up here. All right, one last thing, directional hypothesis. Again, just don't do a directional hypothesis. Do not do a one-tailed hypothesis, but just to excuse me, just to be able to talk about that hypothetically. We'll go through that very quick. Okay, so, directional hypotheses is going to be the same as what we've been doing before. State your null hypothesis, state your alternative hypothesis. This is what I mentioned in class. It needs to be mutually exclusive and comprehensive. So if your alternative directional hypothesis states that it's going to decrease alertness, but it's not going to be equal to the population alertness score, you have to do less than, right? Not less than equal to. So that means the null hypothesis has to be greater or equal to 50. So just make note of the precision here in what you have to do. You select an alpha level and one tail because it's your directional test, right? So you're going to be looking up a different column in the t distribution because we're not doing two-tailed, we're doing one-tailed. First, I have to locate your degrees of freedom. So if your sample is 9, that'll be 8. So we look here, proportion in one tail that corresponds to 0.05, and we run down until we hit 8, which is going to be 1.86. So I'm not going to go through that whole thing as far as that example that we used, but you can calculate your t statistic, and is your t statistic larger than the critical value, right? In this case, this is also where I say it's important to sketch it out, because even though it's a negative value here, you're saying that this is the population. I can't keep my mouse straight. This would be the population mean. My alternative hypothesis says that I'm going to be less than. So you're actually looking for a negative number here, right? This is an absolute value, so it can be negative or positive because we're either talking, it's symmetrical. You're either up here or down here. You're either down here or up here. So for degrees of freedom of 8, that t distribution, you have to basically beat the 1.86, and with 2.67, we are definitely there. We're going to be somewhere down here. So we can safely, even with a directional hypothesis, or not even, with this directional hypothesis, we also reject it. Which again, do not do a directional hypothesis, because it's always going to be easier to reject the null hypothesis with a directional one, with a one-tailed, because your t the critical value for t, or z, if we're doing the z statistics, is going to be smaller. So it's easier to like get something significant out of your data. All right, guys. So that was chapter 9. Effect size, a new R-squared, a new way of looking at variance, a new way of looking at effect size through variance explained from your treatment. We talked about confidence intervals when you don't know the mean, but you can say, I think it's going to be somewhere in here. You use the t to calculate that. And then the last part was directional hypothesis. Okay, so Thursday, we're starting chapter 10. And we'll see how far we go there. But yeah, we got only 2 more chapters left. And then after Thanksgiving, we're going to be doing lots of practice with SPSS. I'm going to work with you individually in class to figure out how you need to set up your data to properly do the statistic that you need, because it's going to vary. Some of you have within subjects design, some of you have between subjects design. So you're actually going to use a different t-test. And that's what we're going to start talking about tomorrow. For me tomorrow. For you guys, whenever you watch this, Thursday, the next class. All right, guys, I will see you then. Bye.